welcome to this lecture. If you recollect, over the last few lectures, we were looking at some real time task scheduling algorithms. Initially, we looked at simple simple clock driven schedulers, and later we have been looking at event driven schedulers. Initially, we looked at the EDF, and then we are looking at the rate monotonic scheduler. And in the rate monotonic scheduler, we saw that the scheduling algorithm is really simple. It is a preemptive scheduler, and we need to assign priorities to tasks based on their frequency of occurrence or their period. And once we do that, we can do some mathematical analysis to say that if a task set will meet its deadline. And we looked at three important results. The first is that utilization must be less than 1 for a task set to be schedulable, but that was a necessary condition, not a sufficient one. But then we looked at the sufficient condition, the Liu Layland condition, n into 2 to the power 1 by n minus 1. We looked at the expression and saw that the utilization should be less than that for a task set to be schedulable. But then we said that that is a pessimistic condition, because even if a task set fails the Liu Layland condition, still it may be feasibly scheduled. And then we looked at the Liu and Lehoczky's theorem, and we are trying to do some examples. So, let us start from that point. One was that we said that the main idea behind the Liu and Lehoczky's criterion is that in the worst case situation, which occurs where all tasks arrive together, if the tasks meet their first deadline, then the tasks will continue to meet their deadline under all phasings. If we recollect the exact wording of the theorem, that if a task set meets its first deadline in the 0 phasing condition, then the task set will meet its deadline in all possible phasings. And we are trying to check graphically whether a task set will meet its first deadline, but that was bit cumbersome. And we then looked at a mathematical expression which will tell if a task set meet its deadline. So, the mathematical expression is given as for a task T I, the first deadline will be met if E I plus sigma j equal to 1 to I minus 1, ceiling of P I by P j into E j is less than the task period. The intuitive idea behind this expression, we had seen that whenever there is a higher priority task, the task cannot run, its higher priority tasks will run, and the time for which the higher priority tasks will run on 0 phasing, that is the task arises in phase with its higher priority tasks, is given as ceiling of P I by P j into E j. For example, if the task period is 20 and we have a higher priority task whose period is 7. So, then 20 by 7 ceiling will be 3. So, 3 times at most P j can occur within P I, which is 20, because they occur once at 0, once at 7 P j will occur, and again at 14 P j will occur. And therefore, we can generalize that for any higher priority task Pi pi p j ceiling into E j, because each time P j the task j occurs, it will run for E j time. Ceiling P I by P j into E j, that is the time that will the higher priority task T j will run, and that will have to be considered for all higher priority tasks, that is j equal to 1 to I minus 1. So, for every task T I, we need to check if this condition holds. If this condition is okay for every task, then we can say that the task set meet its deadline. So, now let us look at some examples based on the Liu Layland and Liu Layland's expressions. The first example we consider here is 3 tasks T 1, T 2 and T 3. And for T 1 the execution time is 20 millisecond and the period is 100, E 2 is 30 millisecond, period is 150, and E 3 is 60 millisecond and P 3 is 200 millisecond. By the rate monotonic analysis, we have to give the highest priority to T 1 because its period is the shortest, next highest priority to T 2 and T 3 is the lowest priority. Now, let us check whether with this priority assignment of the rate monotonic scheduling, the task set will meet its deadline. The first thing we check is the Liu Layland criterion. We compute the utilization due to various tasks, and for the first task it is 20 by 100, 30 by 150 for the second, 60 by 200 for the third task, and we get 0.7, and that is the total utilization due to the tasks, and we need to check whether the Liu Layland bound is satisfied by this, and the Liu Layland bound for 3 tasks is 3 into 3 to the power 1 by 3 minus 1. So, that is n into 2 to the power 1 by n minus 1. So, if you simplify, you will get the Liu Layland bound to be 0.78 and the utilization of the task set is less than 0.78, and therefore, straight away we can say that the task set will meet its deadline. The Liu Layland criterion is satisfied and the task set is schedulable, that we can infer. Now, let us look at a different task set, where the first task is 20 millisecond execution time, 100 millisecond is the period. Second task 30 millisecond is the execution time, 150 millisecond is the period, and the third task is 90 millisecond is the execution time and 200 and okay. So, let us check the utilization. So, 20 millisecond out period is 100, second task is 30 millisecond, period is 150, and the third task is 90 millisecond and the period is 200. So, the utilization is 510 by 600, which is 0.85, and the Liu Layland bound for 3 tasks is 0.78, and this exceeds the Liu Layland bound, and therefore, it fails the Liu Layland test. So, according to Liu Layland, may not be schedulable. But then we know that Liu Layland is a pessimistic result. We need to check the completion time theorem of the Liu and Lehoczky to say that whether it is schedulable or not. The first thing is let us look at the Nave approach, where we graphically plot whether the tasks, all the tasks meet their first deadline under 0 phasing conditions, and if all the tasks meet their first deadline under 0 phasing, then the task set is schedulable. So, let us start with task T 1. T 1 is the highest priority task, and even if it occurs with T 2, T 3, T 1 will run and it will complete by 20, whereas the deadline is 100. Therefore, T 1 meets its first deadline. Now, let us try for T 2. T 2 takes 30 millisecond and 150 millisecond is the period. So, the first instance of T 2 must complete before 150 millisecond, and since T 1, T 2, T 3, T 1, T 2 occur together, first T 1 will run, and as T 1 completes, T 2 will be taken up, and T 2 will run up to 50 millisecond, and by that time it will complete, but its deadline is 150. So, well within the deadline T 2 completes, because the next instance of T 1 will occur only at 100. Now, let us look at the third task. Requires 90 millisecond and the deadline, the period, both are 200 millisecond. Now, let us again graphically plot. So, T 1, T 2, T 3 arrive together. T 1 is the highest priority, that runs for 20, and then T 2 runs for 30, and at this point T 3 can start to run. So, T 3 can run up to 100, because at 100 T 1 would again, the T 1 instance will arise. So, by that time T 3 would have completed 50 millisecond of execution, and after T 1 completes, again T 2 can execute, and finally T 3 executes and completes, but that is well within its deadline. So, the task set meets its deadline, we can graphically plot and check. Both T 1, T 2 and T 3, all of them meet their first deadline. Now, let us do it mathematically. So, again we have the 3 tasks 20, 100, 30, 150, 90 and 200. So, first let us check the Liu Lehoczky's condition for the first task. T 1 is the highest priority task, and it will not be preempted by any other task, and therefore, it will run for 20 and it will meet its deadline, because the deadline is 100. So, 20 is less than 100, and this ensures that T 1 would meet its deadline. Now, let us check for T 2. T 2 would need 30 millisecond, and T 1 is its higher priority task. There is only one higher priority task, and that can arise 2 times, because 150 by 100 ceiling is 2, and each time the T 1 task runs, it will take 20. So, we have written 20 into 2, and that gives us 70, and that means that T 2 will complete execution by 70 millisecond, whereas the period is 150. So, even in this case also the Liu Lehoczky's criterion is satisfied. Now, let us look at T 3. T 3 requires 90 millisecond execution time and its period is 200, and the task T 1, the highest priority task, can occur twice, because 200 by 100 ceiling is equal to 2. So, 20 into 2, 40 millisecond will be taken up by the highest priority task. Now, the second highest priority task is T 2. It will also occur 2 times, because 200 by 150 ceiling is 2, and each time T 3 occurs, it will execute for 30 millisecond. So, the total works out to be 190, which is the same as we got in the graphical sketching, but here these are simple expressions, we can easily do it quickly without any mistake, whereas the graphical one is prone to mistake and also takes lot of time. So, from now onwards, all our examples we will use the mathematical expression directly. The graphical solution helps us understand how the Liu Layland's criterion works, the main concepts behind the Liu Layland's criterion, but to really work out the solution we will use the mathematical expression. So, from the Liu Layland's criterion we can see that the task set is schedulable. Now, there is a practice problem, please do it on your own. We have 3 tasks. T 1, the execution time is 10, the period and deadline both equal to 50, and the phase is 100 millisecond, all are in milliseconds. The task T 2, execution time is 20, the period and deadline is 60, and the phase is 0. And task T 3, the execution time is 30, the period and deadline are both 80, and the phase is 50. So, please try this, check the Liu Layland condition whether it is schedulable, and if it is not schedulable according to Liu Layland, then before concluding that the task set is not schedulable, we need to try the Liu and Layland's criterion. But just asking this question, that suppose a task set fails the Liu Layland's criterion and also the Liu and Layland's criterion, then can we safely conclude that the task set is unschedulable, or is there a chance that the task set is still schedulable? The answer to this is that even when a task set fails the Liu Layland's criterion, still it may be possible that it may meet its deadline. The main reason behind this is that in Liu Layland's criterion, we check the worst case condition, where a task arrives in phase with all its higher priority tasks, but then for a given task set it may not occur. The 0 phasing of a task with all its higher priority task may not occur, and that is the reason that it may fail the Liu Layland's criterion, but then it may still meet its task deadlines, but then these cases are very less, that a task set fails Liu Layland's test and still meet its deadlines. Now, let us look at some issues in rate monotonic scheduling. The first thing that we want to check is about a very severe thing that we talked about in the EDF scheduling, is the transient overload. The transient overload, if you remember, we had said that sometimes a very low priority task like task result logging or some health monitoring, checking, etc., these are low priority tasks, and if some of these tasks get delayed due to some reason, then that may affect the highest priority most critical task. If a lowest priority task cannot affect the higher priority tasks, then we say that the system is stable under transient overload. But if the lowest priority task, when it gets delayed, can also delay the highest priority task, then we say that the system is unstable, poor transient overload handling capability, which was true in case of EDF. Now, let us examine for the rate monotonic scheduling. So, here we make a statement here that the rate monotonic scheduling is stable under transient overload conditions. The rate monotonic algorithm is stable under transient overload conditions. But then how do we argue, how do we show that it is really stable? Can you think of something that will help us convince that the rate monotonic scheduler, the lowest priority task, cannot make the highest priority task to miss its deadline? The answer is very simple, because here in the basic rate monotonic principle is that a higher priority task will be taken up for execution when it is ready, even when a lower priority task is not completed. So, it preempts the lower priority task. There is no chance that a lower priority task will continue to run when a higher priority task arrives, and that conclusively shows that rate monotonic scheduling is stable under transient overload, because whenever a higher priority task arrives, even when a lower priority task has not completed, that will be context switched and the higher priority task will run. So, the lower priority task must yield the CPU to the highest priority task, to the higher priority tasks, and this is contrary to what used to happen in EDF. And therefore, this is a very positive feature of the rate monotonic scheduling, and it scores over the EDF algorithm as far as the transient overload handling is concerned. The next thing we want to discuss is that how is the rate monotonic scheduler implemented. A very simple implementation without much thought can be to keep all the tasks in a queue. So, in the queue, as the tasks arrive, we keep it at the queue, and each time either a task arrival or completion event occurs, we need to check through the queue to see which task has the highest priority of the all the waiting tasks in the queue, which task has the higher priority. But if we analyze this situation, then insertion, when a task arrives, we keep it at the end of the queue, and therefore, insertion time is O1. But then on each scheduling point, that is on a task arrival or completion, we need to check the entire queue to find which has the highest priority among the waiting tasks, and therefore, this is O n if there are n tasks waiting in the queue. Not a very efficient solution. But what about a priority queue? A priority queue can be implemented based on a heap. I think you know that a heap can be implemented on an array, and we use a array data structure to have a heap, and in the heap the insertion is log n. If you look at the heap algorithm, inserting an element into a heap is O log n, whereas the highest priority task can be obtained easily, and that is O 1. But you can see that this is a better solution than a linked list, more efficient, but then still it is not good enough, because at each scheduling point we need to, if a task arrives, we need to insert the task in the heap, which is log n. Can we do better? Yes, we can use a multi-level feedback queue, and this is the one which is actually used in the operating system implementations of a rate monotonic scheduler. The idea here is that we allow only a fixed set of priority. A little later, after a few classes, we will look at the POSIX real time standard, and we will see that the number of priority levels that are available is typically 16, and in some cases we will see that it is 32. So, if we have a fixed number of priority levels, then we can have a queue here. So, priority 1, if it is assigned to a task, each time the task arises, we insert it in the queue, and after it completes, we keep it waiting, and until again the task period is over, we insert a fresh instance here, and that we do for all task priority levels. So, if you check here, the insertion is O 1, but what about selecting the task on a scheduling point? The selection is also O 1, because we need to check from the highest priority task and check if there is a task in any of these queues. So, if there is any task in a queue starting from 1, the scheduler looks through, and in whichever queue it finds that there is a task waiting at the front of the queue, it just takes it, and that is O 1. And since there is a limited number of task levels, and therefore, it just needs to look for up to a certain limit, and therefore, both insertion into the task queue and also getting a task from this, both are O 1, a very efficient implementation, and therefore, as we discuss the real time operating system implementation, we will see that the rate monotonic scheduler is typically implemented with a multi-level queue, and all real time operating systems, they support real time task scheduling through the rate monotonic scheduler by providing a fixed set of priorities. At this point, getting close to the time, we will stop here. Thank you.